Thanks everyone and good afternoon. I'm Salvatore. I'm a research assistant professor at Northeastern University in Boston, Massachusetts. And I primarily work with the Institute for the Wireless Internet of Things, which is an institute that we created a couple of years back. And it's kind of coalescing all the strands of Northeastern University in the field of wireless networking. And it basically, what it does is kind of like bringing together different faculties working in the domain of wireless networking, AI, optimization, and how to usually in general improve wireless networks. And quite recently, we are kind of like focusing primarily on cellular networks, 5G, 6G, and now we have been working for a while on Open RAN technologies. And this talk will be primarily about Open RAN with specific focus on O-RAN Alliance standardization, and we will be discussing some very high-level overview of the architecture being proposed, what are the challenges, and how specifically tailored for AI for cellular networks. And we'll be discussing some experimental platforms and how we can actually develop AI that can run in real time on a cellular network. But the work that I will be presenting is a joint work with my colleagues in Northeastern. I really thank them, and also some funding agencies from the US government that made it possible to kind of like work on those technologies and develop a new one. So basically, let's start with what is really happening in the cellular domain. So we are kind of like coming from a traditional environment where all the base stations are considered as black box, where all the functionalities that you find usually in a base station are lying inside one block of hardware. You see like RCC, SDAP, MDCP, and RF, physical layer, MAC layer, they all live within the same hardware. Now we're moving towards more open, programmable, and virtualized cellular networks. And that means that the network is being disaggregated. It's being executed primarily via software. And those functionalities are now being moved to a bunch of components, which in this case are called the centralized unit that hosts the higher level of the protocol stack, the distributed units that primarily host like layer 2 and low physical layer functionalities, and the radio unit, which is basically where the antennas live. And if you see here, all the blocks that were kind of like living inside one single, all the functionalities that were living inside a single block, now they've been distributed and they can be instantiated using software containers, microservices, and they can be executed at different places of the network. That can be the edge cloud, or it can be the actual cloud, or it can be on-premise at the cell site. And in this specific domain, the O-RAN Alliance, which is an alliance that consists of both telco operators, manufacturers, and different industry partners, as well as academia, is trying to find a way to standardize the way the Open RAN should operate in the next few years. And what they're doing is exactly trying to find out what's the architecture, what are the open interfaces and standardized interfaces to be used. You see here, basically, this is the architecture. To the bottom right corner, you see the CU, the DU, and the RU. Those are actually the G0B components, and they are disaggregated. They connected with different interfaces. And then you actually have all those interfaces like the O1 interface, A1 interface, E2 interface, that are interfaces that are being standardized by the O-RAN Alliance. And they're used to collect the data and from one component to the other one, and to let them talk with each other. And the reason they're called open is primarily because as of now, what happens is that if an operator buys a Nokia component, then for that specific area, all the other components have to be Nokia or Ericsson components. So if you buy Nokia, then everything else would to talk with Nokia equipment. The reason why they're looking now at open interfaces is that they can start looking at multi-vendor deployments. So that if you buy a Nokia base station, it can talk with Ericsson base station or a Mavenir base station or any other base station coming from any other vendor. And since all those components here, like the CU, the DU, and the RU are disaggregated, having open interfaces that are being used by everyone lets you buy a CU from one vendor, a DU from another vendor, an RU from another vendor, and you can use the very same interface to let them talk with each other without any performance degradation. The other components, again, is the disaggregated RAN. And of course, it's really open towards getting open source contributions, because the goal is really to have an infrastructure that can be extended, it's customizable, and everyone can use. But the most important components, I would say, are the RAN intelligent controllers. Those are they're called the RIC. There are two RICs. One is the no real-time RIC, and we will see what it does, and the near real-time RIC. As the name suggests, they pretty much kind of like deal with different timescales. They're called intelligent controllers because that's where you want to run your intelligence. It can be optimization, it can be heuristic, it can be in AI, machine learning, deep learning, you name it. All the intelligence will run within those two components. If it's a non-real-time timescale, which usually means something higher than 1 second, will run inside the no real-time RIC. If it's something that is more near real-time, and we will see what that means, it will run here inside the near real-time, which is closer to the base stations. To give you an idea of why they're having two different RAN intelligent controllers, this table kind of summarizes what are the control parameters that you can consider. For example, the no real-time RIC will handle thousands of devices. We'll get input data that are infrastructure level KPIs at timescales that are usually higher than 1 second. So for example, you can control slicing policies, you can control the policies or the models that you want to deploy or you want to train. And usually that's something you would do at a timescale higher than 1 second. So that can be something you do every 10 minutes, every 5 seconds, every hour. That is something that is considered not real time. So for example, if you want to turn on or off a base station, that usually is something that takes more than 1 second. That's something you want to do here in the no real-time RIC. You can move as well intelligence to the near real-time RIC, which is this component here. And here instead, since we are operating at timescales that are between 10 to 1,000 milliseconds, what really happens is that you're working with KPIs that are usually related to the number of sessions that are active at that specific time, how many PRBs, the physical resource blocks are being used, what's the size of the buffer. And you want to use those KPIs to control, for example, load balancing or handover, control mobility, or scheduling policies or run slicing. So those are all things that usually are kind of like embedded within the near real-time domain, and they will execute inside the near real-time RIC. Oh, by the way, I didn't mention it, but anytime you have any question, just feel free to stop me and ask for clarification. I'll be more than glad to take questions online. The last loop is the real-time. So we move from non-real-time to near real-time to real-time, and the real-time intelligence is basically where you get KPIs pretty much instantly, and they're kind of like giving information about what's the channel state. That changes very fast. Or what, for example, you can handle IQ samples. Those are things that usually you get in the order of less than 10 milliseconds, even microseconds. For example, IQ samples. You can use IQ samples to detect what's the best beam or detect where the beam is coming from. And you want to do that as fast as possible because users are moving, the channel is changing rapidly. So you want to find where the beam is coming from. Or for example, you want to do spectrum sensing and you want to use the IQ samples. Those are things that usually operate in the real-time domain. And for example, you can change modulation, you can change the actual scheduling at the TTI level, and so on. So there are three different control loops. The first two, the no real-time and the near real-time, are being standardized by ORAN. The last one is left for future studies, because that's something that requires manufacturers like Nokia and Ericsson to really open up their base stations, which is something that they are very, it's not something that is going to happen in the near future, because that's where the intellectual property lives. So there is a lot of patents there. So that's probably the reason why they have left it for future extensions, because that's where really it's hard to convince manufacturers to open up their base stations for those specific functionalities. And if we look at all those control loops, we kind of like move forward toward why now we need AI and we need intelligence in Oran. Because we have seen that we basically can control different things in the network at different timescales. So far, with traditional networks, all the control is not really intelligent. It's really, most of the operators or even the manufacturers, they use heuristics. So they have simple if-then policies. They are nested trees. For example, if the threshold is higher than a value and there are other conditions, then they select specific actions. The goal with Oran instead is to use AI directly to take those decisions and to use optimization or data-driven optimization in general to kind of like drive the cellular network so that we can really adapt to changing network conditions, and we can move forward from heuristic and we can start really optimizing the network. As a research community, we have been doing a lot of research over the years to optimize cellular networks. The thing is that it's very hard to bring that innovation into cellular worlds because it's been closed so far. Now it's being opened up, it's being software-based, and now we are the chance to bring optimization and AI to the cellular world. And the other thing is that cellular networks are, of course, complex. So it's very hard to find a model that is accurate enough to capture all of the tiny details of a cellular network. We can use Shannon capacity, we can always use different formulas, the beta error rate and things like that. They are theoretical, but they will not really match what the cellular network is doing at that specific time. So we can really, in this case, use the data coming from the cellular network to use AI so that we can do model-free optimization, so that we extract the model from the data. And the way we do that in Oran is through software applications. So rather than, so far, all the logic is pretty much a piece of hardware embedded in the base station. Now, all the logic will execute as software microservices or software containers, and they will run as our apps if they run inside the Northeastern brick. So our apps are just like a fancy name to name any microservice that run within the Northeastern brick. Xapps if the intelligence run within the Northeastern brick. And we have also introduced the concept of DHapps, which is basically a software container that runs directly at the CU and the DU to perform real-time inference and control of the network. For example, beamforming. You can do beamforming with DHapps. Or if you want to really control the scheduling, you can do the scheduling control with DHapps. Or spectrum sensing, you can use DHapps.
I have just a question on the figure.
Sure.
DHapps, I understood it is distributed applications, but what is X and R?
Yeah, so R, it kind of like comes from, they've been just like chosen, I think randomly from the Oran community. We inherited our apps and X apps. We only picked the apps because we thought it was fancy to call them distributed because they run directly the base stations. But for the other two, they come up with those names, and okay. I don't know where they took it from.
Just a good curiosity for myself.
Yeah. Okay. So if we look at how, I mean, the thing is that operators are really trying to find a way to embed AI in their network. So they're kind of like come up with an architecture that covers all the aspects of generating and creating AI. And usually when we want to kind of like deal with AI, what we do is first we need data. So we have this Oran infrastructure, meaning that those are all the base stations or the software components, the rigs, they create the data. And the data usually comes from the interface A1, O2, or E2. I won't go into the details of the interfaces. Those are just interfaces that to collect the data. Once you have the data, then you do the preparation of the data. Most of the time, you just do the labeling or you do the processing. You can, for example, remove data that is not correct, or it's misleading, or is mislabeled, or is just partially not available. And you can reshape the data so that you can create a data set. And then you perform the training. So now you can train the AI. And the thing is that Oran doesn't let you deploy a model on a production network that is not trained already. And that is something that we will discuss kind of like later on in the presentation. The reason why they don't want to do that is it's very dangerous to have untrained AI working on a production network. So it's fine if we do that on our computer or on our cluster. That's perfectly fine on our emulation environment because it's not dangerous. But no operator will ever let you train a model from scratch on a network that is serving users. So one of the principles of Oran is that there is always some sort of offline training to be executed first. Once the training is there, you can deploy the model, you can fine-tune it online, but the model has always to be pre-trained to some extent. And that's what they have here. So basically we do the training part, then the training, you move to the validation of the model. Validation is primarily like a way to test the model, make sure that whatever performance are being delivered by the model are good enough. If it's, of course, if it's not ready, it's being retrained, otherwise it moves to the publication phase. Publication means that it gets published to a catalog. When it's published, then it's ready to deploy. The deployment is basically creating the model, taking the model and put it into one of those apps. It can be an R app, an X app, or a D app. And the deployment exactly means that you take the model, you embed it into the software container, you can deploy the software container, instantiate it, and then it gets executed. And usually this container executes inside what is called the inference host. And that's basically where the model will run. And the nice thing about this model is that you can still get the data online. You can still also use data coming from the offline data set. You can combine them if you need to, and then you can perform the inference and send the inference to the base stations. For example, if you're executing a model to control scheduling or to control beamforming, you can have an inference host here, take decisions, and then the decisions are sent to the base stations, and they can, for example, know where the beam is coming from. Another part that is kind of like very important is the continuous operation block. And that's where operators are very, very interested into kind of like seeing what the AI is doing, like monitoring the AI. Is the AI performing properly? Are we getting the right performance? Is the AI taking the right decisions? If not, can we find what are the vulnerabilities, what's not going good, and can we retrain the model? And that's what the continuous operation block stands for. And that's something that they really care about, because they don't want to use AI just to use AI. They want to make sure that any AI they're using is actually being outputting the right decisions. So now that we have this overview of what Horan does and how AI kind of like plays a role, there are a bunch of things that as a community we have tried to kind of like address and try to solve. And that's what has been our goal in the research that we have been doing here. So first, it's very hard to get data from operators. Business can be behind the reasons why not to get the data. Security is another issue because getting the data out of the operator is kind of like something that can be related to a security vulnerability. So where do we get the data? Because if you want to train AI, we need a lot of data. Another issue is that once we deploy the AI, we need to make sure that the AI is taking the right decisions. So we need a tool to kind of like make sure that the AI is taking those right decisions, and we need a tool to test the AI. And of course, the other thing is when we deploy AI, and if you think about like any network operator, they have base stations pretty much everywhere in the country, but each area is usually different from another one. For example, if you move downtown in a city, then users tend to be there pretty much every day, all day. But if you go to a rural area or a residential area, users are there pretty much during night or during the weekends. So what happens is that it's very hard to kind of like determine, you don't want one model for each area, for each different portion of the day. You ideally want AI that is able to kind of like operate under any deployment, any traffic condition, any network condition. And if there is any change in any of those aspects, the AI still has to operate. And that's the problem of general AI. How can we bring general AI to the cellular domain? And while in computer vision, this is a problem that usually it's not really, it's something that is kind of like already, they know how to tackle it, because you can afford most of the time, even minutes for the inference. You feed pictures, those pictures, you can take time to detect what's there. But once you start moving to the cellular domain, where you have to take decisions at the millisecond level, and those decisions has to be the most accurate ones and the best decisions that you can take, it's very, very important to make sure that the AI is general enough to operate under any possible condition. So I will go through all of those different challenges and we have solved them. So first, we need large-scale data sets. And we are lucky enough in the US that I think that there is going to be probably definitely something in Europe. I'm aware of different European projects. We have the Power Platforms and Colosseum. Yeah, I'll give you some details about Colosseum and the platforms later on. So those are platforms that are open. Those are test beds that give you the possibility to instantiate cellular base stations on demand and run experiments without actually going to interfere with what operators are doing. So you can instantiate your own cellular base station, usually using Open Interface or SRS-RAN. You can instantiate the base station, perform the data collection. You can play around with different scheduling decisions, slicing policies, and so on. You can collect the data, you can process the data, and you use the data to train the AI.
I have a question.
Yeah.
What do you mean by instantiate your base station? Is it a simulation or something like that? Or?
No, it's actually instantiating an actual base station that you can see with your own smartphone. I don't know if you're aware or if you're familiar with SRS-RAN or Open Air Interface. Those are open source softwares that if you have a software-defined radio, you can run the software and interface it with the radio to instantiate an actual base station that you can connect with smartphones. So basically, you can do emulation as well, but this is something that runs in real time and you can see, and with the base station transmitting over the air.
Yes, so at Telecom Chipari we do so, but of course we cannot collect any data set because we have one phone, maybe two, maybe we can have even 10, but it will not be representative of a real network.
Yeah, so the nice thing about those software is that you can scale them. For example, we have developed this platform, it's called Scope. And this comes with tools to collect 30 different KPIs. Of course, it's not going to be the same network that AT&T or Orange or Dutch Telecom is using on the field, but you can still see how the cellular network is operating and see, for example, what's the load, what's the buffer size, and so on. Of course, that's still, there is a mismatch between what the operators are doing because they're handling thousands of users. With those softwares, you're probably working at a smaller scale. So there is a mismatch, but the operations are still the same.
Okay.
And we are pretty lucky at Northeastern. We have access to a variety of different test beds. So we have Arena. That's a test bed that we have here in the lab. Those are 64 antennas. You can use any of the devices we have with software-defined radios. Any software-defined radios can operate as either a UE or a base station. You can change the topology. You can instantiate different networks, and you can collect the data. We also have a drone cage and anechoic chamber we usually use to kind of like experiment with cellular networks and drone application with flying UAVs. There is also Colosseum, and I'll give some details in the next slide, and a bunch of other test beds that are primarily for millimeter wave and terahertz. as well as the power platforms. Those are over-the-air platforms with antennas, usually on the ceilings of tall buildings, with the radios or at different locations in the city, so that you can kind of like deploy a cellular network and get the data for an outdoor environment. So all those different test beds, we usually use them to get the data under different environments with different traffic profiles, different topologies, and different challenge conditions. And I just want to give you a little bit more detail about what Colosseum is. So Colosseum is the world's largest RF emulator. So it's a very large data center. It's using all the microservices and container-based deployments. But the nice thing is that it uses 256 software-defined radios, and you can use them as either base stations or UEs, so that you can instantiate a very large cellular network. And the nice thing is that those radios are transmitting actual waveforms, but they are not transmitting over the air. They're transmitting over cables, and they're connected to this module, which is called the massive channel emulator. So basically what happens is that the radios are connected to a channel emulator. So they transmit waveforms. Waveforms go over the cable to the emulator. The emulators applies different channel conditions, and you can control what those conditions are. And basically, it's like that the radios are operating in the wild, but you can control how the channel behaves on a millisecond level. So you can basically, for example, we are just showing here some possible deployments that we have considered, but you can, it's virtually possible to do any sort of deployment. For example, those blocks are the different base stations in Rome, close to Colosseum, the actual Colosseum in Rome. You can get the GPS coordinates of those base stations from OpenCell ID. There is another deployment here in Boston, another deployment in Salt Lake City in Utah. So you can create those scenarios. You can use ray tracing to compute the channel conditions. You can load those into Colosseum, and the radio will behave as if they are actually in Rome, with nodes maybe walking around and connected to the different base stations and moving from one place to the other one. And that's what MCAM does, emulating the channel. So you have the radios transmitting, but the channel it's the only thing that gets emulated. And you also have a tool that gives you a possibility to generate different traffic profiles. When we say traffic profiles, for example, you can generate video streaming profiles, you can generate browsing, emailing, texting. It can be just like a file transfer sort of traffic. You can create all those things. And the reason why those things are useful is because you can really get a lot of data under different conditions, being that traffic conditions or being that channel conditions. We collect the data and we use that to train the AI.
I have a question here on this slide.
Yep.
So I understood that the communication through air is emulated. And my question is, has the simulator been calibrated with real data, or just calibrated compared to what is expected theoretically?
Yeah, so we actually have a project that, and our colleagues have demonstrated that. So they took channel measurements from an actual deployment with moving cars. They got that from the Department of Transportation. So they got the actual channel measurements, then they recreated the same scenario using ray tracing softwares in Colosseum. And then they compared the channel condition with what the ray tracing is saying with the actual measurements that have been measured. And they saw that they match. So basically, you can really get very accurate channel emulation capabilities with Colosseum. And that is something that we were looking forward to those results, and we were glad to see that there is a match. But the nice thing is that you don't really, you can either go to the realistic path, but you also have the capability, for example, if you're doing some theoretical work and you're doing some asymptotic analysis and you want to, for example, test different statistical models for the channel, like Gaussian or AWGN or the one Rician or Riley, you can create scenarios using those distributions. And then you can use the distribution to pilot the radios, you can kind of like use that as well. So you have the flexibility to use either if going really realistic or follow models to validate your theoretical results.
Okay, thanks.
Maybe another question. So is the emulator also considering the profile of buildings and all these details? Or
Yeah.
okay.
Yeah, there is one of, for example, that scenario that I mentioned with the cars. It's actually cars moving in a I don't think it's a highway. It's just like a smaller street, and there are buildings across. So what we usually do is we get the map from Google Maps. We get the 3D model. We create the 3D representation in the ray tracer, and then we run the ray tracing. We create the channel, and they all consider the reflections with buildings and the different topologies.
Okay.
Okay, so now that we have all those tools to get the data and to test, the other thing is we get the data. How do we actually train the AI, and how we test the AI and see what's really happening? And that's something that we have developed and we have released as open source to the community. It's called Open Run Gym. So that's you can visit the website here for more details. We have a bunch of publications with results and some theoretical analysis as well. That's something you can basically download from the internet. And also, I'll give you more details now. And it's actually something you can use to test and play around with the AI for the Open Run. And it covers all those aspects, from data collection to the training to the testing. And that's what Open Run Gym is. So first, it gives you a neural TMRIC implementation on Colosseum. It can actually be exported out of Colosseum with a few tricks, and it's already compliant with ORAN specifications. It actually comes with data collection and control capabilities. So not only you can collect the data sets, but you can also have APIs to control the base station. It comes with the programmable stack for the base station. So not only you have the APIs, but we have extended SRS-RAN and open interface so that you can enforce control decisions at each layer of the protocol stack. That is open source, so it's extendable. So usually what happens is that if a feature you want to control is not there, you can basically extend the code and add it, and you add the API, and then you can control that in real time. And the reason why this is important is that the way those SRS-RAN and open interface have been designed is that every time you want to change something, like you want to change the scheduling profile, or you want to change the slicing profile, you need to re-instantiate the base station. So you have to stop the code and re-instantiate the code. What we did instead is to not only add those functionalities, but give you a possibility to change them in real time without having to re-instantiate the base station. That was something that was not there, and it's something that we struggled first, and then we say, okay, let's make it and release to the community. And there are a lot of people using this at the moment. And the other thing about Open Run Gym is that it's already integrated with the experimental platforms that I mentioned before, that Colosseum, Arena, and the other platforms. So this is a unified framework to cover data collection, testing, and training of AI. We also extended the tool to NS3 for those that are familiar with NS3. It comes with still neural TMRIC, and it comes with integration with NS3. NS3 usually was not supporting any cooperation with the ORAN real-time RIC, and we created that. And it's actually already, it's open source, and we have released this as well. If you visit the website, you can find more details. Now that we have covered those aspects, the other problem is, okay, how we create the general AI that can operate under different scenarios and conditions? And that's something else that we have developed and released. We call it the Coloran X app. So you can see that as a template that everyone can use to embed AI and test it on cellular networks. So we mentioned that XApps are what ORAN uses for the neural time rec. What we have created is basically a template that comes with two blocks. One is the RIC interface, and that's where you basically get the data in real time. That's where you not only get the data, but you are able to talk with the base station to control and get the data. And then there is what we call the data-driven logic unit, which in this case is a deep reinforcement learning agent that is using, in this case, you have the actual agent. In this case, we are showing just an actor critic network, but you can also embed in chain different AI modules. In this case, we are using an encoder portion of an autoencoder to get the data and then create a latent representation of the data and use it to feed the reinforcement learning agent. The reason why we do that is because we usually deal with too much data, and too much data might create like outliers, things that are not representative, redundant information. What the encoder does is to take this lot of data, compress it, and create a more a smaller representation of that data that it's still representative of the state of the network, but it's easier to deal with. So those are the two different components that I'm just showing here. But this is a template. Basically, if you create your own AI, you can just place it there and you can execute it. To give you some insights on what we have been doing, for example, we have trained deep reinforcement learning agents to control scheduling policies. When we say scheduling policies, means that there are different profiles. You can change, you can select which profile you want to control. For example, you can have a round robin policy, a water filling policy, or a proportional fairness policy. And you can in real time select which one you want to use depending on the traffic conditions and depending on the actual requirements of the of users. Because you can also implement slicing. So you can slice users. You can basically create different traffic profiles. Each will be a slice. Users will be assigned to that slice. And what will happen, you can control how much resources are being assigned to each user and to each slice, and what's the scheduling profile you want to control. And usually the reward, for example, for the reinforcement learning agent that we have considered is, for example, maximizing the rate for enhanced mobile broadband, maximize the number of packets or transport blocks for the machine type communications, because those are sensors. We want to basically maximize the number of information that they can send, and minimize the buffer size here for URLLC. Minimizing the buffer size is a proxy for minimizing latency, because the lower and the smaller is the buffer size, the faster you're transmitting information, so the lower is latency. And without going into the details, we have done a lot of research here on what are the actions, what's the state that we want to consider, what type of input we need. I want to kind of like show you what the testbed looks like, the testing. So we are testing this with 7 base stations and 40, I think it's 42 users. I cannot read this. Yeah, 42 users. And we have implemented this on Colosseum using Open Run Gym. We have Colosseum here. We have the base stations here to this right portion. The users, we have 6 users per base station with 3 different slices. The channel emulator is in between, connected to the traffic generator. And then we have attached the RIC, and that's where we also do the no real-time training of the AI here in the no real-time RIC. Without going into the details of this, I'll just show you there some results. So one of the questions is, how many actions do we have to control? What's the impact of controlling different actions? So I've discussed you like controlling the scheduling or controlling the scheduling and the slicing at the same time. So the agent is taking different decisions with different action profiles. And if you see, basically, the blue line is the line that you get when using AI that only control the scheduling profile. And the orange dashed line is where you basically instead have control both the scheduling and the slicing. Usually, increasing the number of actions should result in a higher performance, because the action space is larger, so there is more room for optimization, and then you can get better performance. If you look here, for example, this is the PRB ratio. The PRB ratio is the ratio between what users are asking and how many resources we are giving them. Ideally, you want to give all of the resources they're asking. If you give them all the resources they're asking, means that you're satisfying that user with one transmission. So you want this curve here, to be to the rightmost corner. And that's what basically happens when you increase the size of the action space. For the number of transport blocks, we would say that we want to transmit as many packets as possible for machine type communication. And also controlling scheduling give you some performance improvement here. When we look at throughput instead, it's something interesting happening. If you look at the blue line, that's the distribution of users. The reason why it's kind of like a staircase is because users might have different transmission rates. And when we move, so it's better if it's going to the right. But what happens here is that when we add an additional action, in this case, this slicing, you see that there are portions of the system that are working with a lower, you're getting lower rates, which will be here, and other portions that will give you higher rates. So basically what is happening here is that we are actually giving more fairness to users. So basically each user will experience on average a higher throughput. So we did a lot of analysis here. I will not go into the details, but for example, what we try to answer is, do we need to use autoencoders to create a latent space representation of the state? How many actions do we have to consider? Do we have to consider all the possible combinations, or do we have only to focus on those that we think are the most efficient? And usually our analysis results show that adding autoencoders actually helps the network. And the reason why it helps is because if you remove the autoencoder, then you feed the raw data, and the raw data most of the time is either redundant or outliers might kind of like confuse the agent. So adding autoencoders actually creates some, brings some benefits. Something else that we consider is that, we said that can we create general AI? So we have trained our AI solutions considering one specific traffic profile distribution. So the traffic follows a specific distribution for the different users. And this plot here gives you the probability that specific actions are being selected. If you see, like, one action is the one that is kind of like, this is a combination of slicing and scheduling, is the one that gets selected usually with the highest probability. But then there are cases where other actions are being selected. And that happens when the traffic profile is basically, we are using the same traffic profile we used during the training. However, what happens when we change the traffic profile? So for example, we deal with users that are generating a completely different traffic profile. Can we do something? And that something is that basically, can we address the problem of AI working under unseen conditions? The solution is using online fine-tuning. And that's what we have developed here. And I'll give you some results here. So what we do is look at this plot to the left. So that's the training, offline training evolution over time. We are showing the loss that's negative. So we expect the loss to go close to zero. We are showing the reward. We expect the reward, this is positive. So we expect the reward to be as close as possible to a high value. And we see that during the process of the training process, both the loss and the reward improve. The problem is that what happens once we deploy this AI in a condition where the traffic is completely different. So if you see here, we move from what we call the slice-based traffic to a uniform traffic. So in this area here, we are completely changing the traffic profile, and we are saying every user will generate exactly the same traffic. You see that not only the loss, once that happens, degrades, but as well the reward. The reward goes to zero almost. And that basically is telling you that training AI on a specific traffic profile is not really helpful, because once the traffic profile changes, the AI is not working fine. So we have implemented this online training procedure that what it does is basically trying to mitigate that and fine-tuning the weights of the network. And if you see, the first thing we do here, we change the traffic, but then we also do the same by changing the testbed. So we take the AI from Colosseum, and as it is, we move it to our over-the-air testbed, another testbed, it's called Arena. And if you see here, the nice thing here is that when we keep the traffic the same, but we change the testbed, if you look at the reward is pretty much constant, same as the loss. And the reason why it's half of what it was on Colosseum is because Arena is a smaller testbed, and here the reward depends on the sum throughput. And since there are less nodes, the sum throughput gets halved, it gets cut in half, because there are half the nodes. So, but it still says, keeps uniform. And here to the right.
Sorry, there is maybe one question from Anastasios. Yeah. Anastasios?
Yes, thank you. So the question is actually, since you are mentioning here this online like training, I find that there is something not clear between what you were presenting at the beginning in the actual implementation of the ORANs and what you are doing here, because you are mentioning that at the beginning that the that these parts of the infrastructure should be already pre-trained.
Yeah.
And now you are proposing an online training. So I wonder when happens what, let's say.
Yeah, that was my I was not clear, probably definitely not clear. So what Oran says is that you cannot train a model from scratch, like with random weights. You can do online training, but you have to start from a model that was pre-trained. And
Yeah,
that's what you see here.
Then okay, then we can train in, I don't know, some artificial data, and then we install it, and then we do online training. This is something that is permitted.
Yeah, that's permitted.
Okay.
And the underlying idea is that basically you have some model that is fairly accurate, that it works fine already, and it's not fully random, and then you can fine-tune that in real time. And just to give you a brief idea of what's happening, if you look at this is the initial part of the training, which will be this action distribution here. You see that when the training starts, which will be the yellow part here, the distribution is kind of uniform. Then after, let's say, when we change the traffic, you see that the actions start changing in distribution. And at the end of the online training, the distribution is completely different. So basically the system is adapting to what's happening to the system, and you see that the action distribution completely changes over time. Something else that we need to consider, and we kind of like, we're still working on this, is during the online training, what happens is that the exploration might bring the AI to select actions that are not very good. And that's what happens here. So when you look at, basically, this is the where the original training started, that's the purple line. Then we started the online training at the beginning, that's the blue line. At the mid part, you see that the performance is very bad. So that's the throughput, and we are reducing the throughput of users in that's very bad degradation. And then once we end the online training, we get to this green curve. So the thing that this plot is showing is that exploring new actions during online training brings a performance degradation. You can see them here. So that's the throughput. So if you see the train model, the blue line, it's fairly stable. But once you start doing the online training, you see oscillation and the throughput goes down. And that's something that as researchers, we need to find a way to kind of like mitigate that, because that's what scares operators. We cannot just simply train online if we cannot kind of like mitigate those losses. So there is a whole body of research looking at digital twins or some sort of supervised online training where you keep training, but you only enforce specific actions at a specific rate. Or you only do online training when the network is not fully loaded, or you only have for a few seconds. It's going to be slower, but it's something that we have to figure out how to actually solve for a production network. Something else that I want to show here is that if we compare what is happening, for example, for the throughput with the offline agent, that's the distribution of the throughput, with the the new uniform traffic, you see that the distribution is different. And basically what's happening is the online agent is giving you better performance. And basically what it's saying is that during online training, we can adapt to the new traffic. But also what is this plot to the left saying is that since the distribution is pretty much the same, it's similar in shape, is not in value, but we kind of like still remember how to behave when there is the original traffic profile that was used during the training. So we are adapting here to the right, and we're getting better performance, but we are not completely losing our what we learned in the past.
There is a question on the chat.
Oh, okay.
Maxime, are you aware of works using Bayesian methods?
Yeah.
I'm
aware of.
You can speak also. Eh?
Yeah, hi Maxime. Yeah, so we are definitely aware of those works. We haven't had much time to look into that. There is something interesting, and we actually push people into kind of like applying those different techniques because it's a very new area of research. Operators are looking into solutions that are reliable, and we need to provide those answers. So that's something that really is worth to be investigated. We haven't had time. Hopefully someone will have that.
Maybe you have someone in mind.
I mean, Maxime will be visiting us in January. So probably it's the right time to start looking into that. Okay. Moving forward. Okay. Another huge problem. Operators, usually they want easy networks. So they know what they need, but networks are so complex, they don't know how to get it, especially with AI. So one of the problems is that operators usually they have requirements like changing scheduling for real-time broadcasting of 4K video in Times Square. That's what they need. Thing is that how to formalize that is very hard. So one of the work that we have kind of like tried to address is trying to solve those 5 questions. What is the intent of the operator meaning? If we have a catalog of AI, what's the best AI to satisfy the intent? And then now that we know what's the best AI, where and when do we deploy AI? And finally, how we actually deploy and execute and manage the intelligence in real time so that if the intent changes, we can adapt to that. We have developed this framework called Orchestra. It's actually tailored specifically for this specific problem. It executes in the no real-time rig. So this is an R app. It performs tasks starting from intent recognition, optimized intelligence placement, and automated deployment, execution, and management of the intelligence. And this is how it works. First thing, operators submit the request. So they, for example, specify, oh yeah, I need this functionality, I need to control slicing, or I need to control scheduling or beamforming at this specific location, and I need to do that in real time or in not real time. We collect the requests, then we have a bunch of optimization that looks at what are the requests, what are the intents, converts them into an optimization problem, and then goes into an AI and ML catalog and selects what's the best AI and tells where and when to deploy that AI. For example, can we get a specific module that control the scheduling? Do we deploy that at the no real-time rig or at the real-time rig? Or we deploy that as a D app at the base station? So those are the things that we control. And then we deploy the actual intelligence using our apps or D apps or X apps. So there is a bunch of optimization that's very complex. I won't go into the details because I'm running out of time. What you need to know is that's an NPR problem. We came up with ways to solve it and to simplify the problem. For example, one of the things that we kind of like consider is that if you look at the optimization variables, apart from those different indexes, this D index that appears twice, those are the number of nodes of the network. So those are DUs, CUs, RUs, near real-time and no real-time regs. So basically the complexity, the number of variables is d squared. And if you see here this plot, for large instances of networks, there is a very large number of variables, and there is no way to solve this optimally. So if we look instead at where the complexity comes from, if you look at the first layer of the network, there is one node. In this network with 2 neural time breaks, there are two nodes here, and then it's 4 CUs. But what it's trying to say, this plot, is that the most complexity and the number of variables come from the leaves of the tree. So that's where the complexity is actually coming from. It's not the architecture itself. It's just that there are too many DUs and RUs, and the complexity comes from there. So we came up with a kind of like a approach. There are more details in the paper of kind of like branching and splitting the problem into different environments. For example, if we consider them as separated, there are 17 devices and 18, while if you look at here, there were 34. And if you, of course, if you do the square of 34 or the square of 17, that's a large difference. And if you scale up the problem, it gets even more different. So without going into the details, what I just want to kind of like show here is that we have developed this system in Colosseum. We have tested it. We use different XApps and DHAPs. The goal here is really, if you have AI that can execute at the base station, do you really need the AI to run at the RIC? Or can you just run it at the base station? And the reason why you want to run it at the base station is that you don't have to transmit the data from the base station to the RIC. Imagine transmitting IQ samples from the base station to the RIC. That's a lot of information to be transmitted. That's a lot of information, usually in the gigabit per second range. You don't want to do that. So you want to use DHAPs to execute the AI directly at the base station. And that's what you see here. Basically, in this plot, what we're trying to show here is that if you bring AI closer to the base stations or directly to the base station, you can reduce the load by 2.4 times at least in just collecting the data. So this is just the overhead only to collect the data. And you're reducing it by 2.4 times. Something else that I will probably... how much time I have? I don't have time, right?
Yeah, maybe a few minutes now. We started a bit late, so
yeah. So very high level overview of DHAPs. We have been working on DHAPs. We have been proposing DHAPs. And now we are trying to have them embedded into the overall architecture. That's the architecture we are proposing. The only thing I want to mention is that, so we have RApps, XApps, and DHAPs. They are distributed along the different components of the network, but there is a big component here, the conflict mitigation here and here, because it's very, something that we need to be aware of is you cannot have all of these AI taking decisions and just instantiate them and let them take decisions, because they might go in conflict. For example, you have one RApp that turns off a base station and one XApp that controls the scheduling. If you turn off a base station, there is no point in controlling the scheduling. Or for example, if you're controlling the scheduling for the same users with two XApps, they will definitely go in conflict. One will select one action, one will select another action. So what it's required, and we started doing some work here, is how to mitigate those conflicts. And conflicts is not just controlling the same action or parameter. There are indirect conflicts. So controlling scheduling affects throughput. Controlling slicing affects throughput. You're controlling two different parameters that affect the same KPI. So you need to be aware that there will be a conflict that is indirect, and you need to find ways to solve that. In the previous paper, the orchestron paper, we provide some solutions on how to solve that, but that's something that's a very active body of research. How to mitigate conflicts between different AI models that are taking different decisions affecting the same network.
There is one question from Anastasios.
Yep.
Anastasios?
Yes. So here the question is the following. You were again mentioning your introduction to the system. You were mentioning that different companies like Nokia, Ericsson, etc., they might be building different parts of the ORAN infrastructure. And so, I mean, I'm wondering, like, how would this conflict mitigation happen if one device or one part of a device, like the DU or the CU, is coming from one company and the other is coming from the other company?
Yeah, that's a very good question. So the goal of the conflict mitigation here really is to monitor the KPIs directly. And even if if the different components come from different operators, what the ORAN Alliance is suggesting is to have fail-safe procedures. So for example, what happens is that if you're detecting a conflict, there has to be a policy to go back to a safe state. And then the manufacturers have to provide functionalities to go back to that state. So even if they're coming from different vendors, they have to support those functionalities so that you can kind of like, once there is a conflict and you detect that, you can go back to a safe environment, or you can lock some XApps and you can kind of like take them out of the decision process. But the goal is to have this implemented in software. So you can really kind of like block some AI, even if it's running on different vendors. Because the environment offered by the vendor should be a software environment that you can interact with APIs. So as soon as those APIs are there, even if they have different format, but as soon as the API is there, you can still kind of like talk with the system coming from different vendors. I don't know if that answers your question.
Yeah, a bit. It's just who takes a decision there? Would it be who takes a decision?
Yeah, so the decision is taken usually at this high level, is usually taken both at the RIC. The decision is taken by, I mean, there is no way a human can detect that, especially at the very real-time domain. So it has to be AI to detect that. That's an open challenge. So how to design AI which does the monitoring, the conflict detection, and the conflict resolution automatically in a reliable way, so that the fail-safe policies can be triggered automatically. That's an open challenge.
Yeah, I understand.
Yeah. So we have done some research, and we have some ways to handle this, but that's a very interesting research problem, how to make that happen in reality.
I understand. It's just that if each device is triggering something and takes local decisions, it will be a big mess, I guess. So this should actually, yeah.
Yeah. Okay. I'll probably skip that slide and I'll go here. So with the open ranging framework that I just described before, there is a lot of research opportunities. It comes from controlling the base stations with AI, creating data sets, performing forecasting, classification, orchestrating the AI. There are applications where you can play around with spectrum coexistence sharing, building reliable and general AI, online training, conflict mitigation, as we mentioned, design and security. And I'll probably just leave here. That's the website. You can visit that. You can contact me offline if you have more questions. And thanks for listening and for being here with me. If you have any questions, feel free to ask.
So thank you, Salvatore.
Thank you for having me.
So we are a bit running of time, so time for one or two questions. Yes, François?
Yeah, thank you for your lecture. Can you hear me?
Yeah.
Yeah. So I was wondering, in view of the cost of this AI, so there are situations where you know the optimal solution, right? For scheduling, for power control, for this and that. I mean, you insisted on AI, but could you replace in this architecture some of these AI decisions by just the implementation of the optimal decision when you know what it is?
Yeah, you can definitely, that's a very good point. In some cases, actually, we realized that there was no AI required, and you can always find the best solution with an if-then policy. And the nice thing about the XApp that I described before is that you can implement that as well. So you can have that if-then piece of code and implement that. So if you know the policy that it's optimal, yes, you can implement that for sure. The idea is that there is no optimal that works for all possible conditions. So you still need to kind of like detect what's the condition and then implement the optimal for that condition. But if you know what's the optimal is, yeah, you can do that. I focus more on the AI because it's the most challenging part, because it comes with no model. So we don't know what it's really doing. And we need to find a way to understand what it's doing and let it do the right thing. But you can definitely use optimization. We have been using optimization for other applications inside X apps.
Thank you.
Welcome.
Is there a question on the bridge? Yeah, ça y est. So
I do have quite a lot of questions, but I guess I'll have to reach him on like email or something. But first, thanks for the presentation. It was quite educational. Well, maybe I'll just ask one of them that kind of wraps up the core of most of my questions. Well, you considered ORAN architecture, but apparently, from what I understand, you're still collecting data from the base station that has all the components, the RU, DU, and CU. And if not, please feel free to refute. And if so, then when you're training your model, how are you syncing the data from different nodes, or like what are the KPIs? Are they like time sensitive, or we're already scratching all the AI methodologies that depend on time? So like,
no, that's a very good point. So basically, regarding the different users and DUs, so we are now extending to the disaggregated profile, so we can get even more KPIs from the disaggregated components. But we get the data that we have is time-stamped. It's for each base station and each user, and there are more than 30 KPIs for each of those. So basically, you get like a CSV, a report for each user that shows like what's the throughput, instantaneous throughput, what's the SNR, the modulation encoding scheme, the CQI, the bit error rate, how many transmissions were performed, what's the traffic demand, and what's the buffer size, and all those sort of things. So usually you get more data than what operators can actually get out of a Nokia or a Ericsson base station in terms of from an operator point of view. You can extend to any other KPI. But yes, we are looking forward into extending that to get more KPIs from a system point of view on each interface.
but
I don't know if that answered your question.
yes, and do you train models per user or for the network? And here comes the autoencoder that kind of wraps up the state of the network, which kind of is a big question. What do you see the state of the network to be? Is it dependent on the type of traffic, or like the number of users who are requesting the traffic, or like the, I know, the bad weather like impacting the path loss or something, or things similar? Like, what is your notion of states that you're like using autoencoders to kind of compact the data?
Yeah, that's another very good question. So the state is one of the most complex things that we struggle a lot finding the right way to represent the state. We find out that we did a lot of data analytics first. I mean, we were first reading like raw data and see what happened. Okay, let's use it as a black box. Then we did data analytics and say, okay, let's focus only on some KPIs that are enough to give a good representation of the network, looking at correlation and this sort of things. At the moment, what we do is we extract from users' reports KPIs that we are interested. For example, you can see that as a metric. We extract, for example, 10 entries from the most recent 10 entries from the report for a specific selection of users. For example, if we know we are interested in one slice, we only get data from users that are generating profile for that specific slice. One slice can be even one user only. So you can, that can be like a premium users. you will extract KPIs only for that user. That is flexible. So we have found out that this give us advantages, and it's already kind of like working fine. But another open question is, can we even use less data, or what's the best data? I mean, we have tested one that works fine, but the question is that the best one, or is just one that we were lucky enough to find that is working fine? It's not optimal. Can we find what's best? Open question. So far, we were lucky enough that it's working. Yeah, but that's something that we would like really to investigate. But the granularity can be up to one single user. And we have AI that works for the entire network, for a specific slice, with multiple users, no matter how many users are there.
Thanks. Well, I do have a lot of other questions, but
I think you will send them by mail. It's better, I think. Okay, I propose to stop here, and if people have more questions, don't hesitate to contact the speaker.
Feel free, yeah, drop me an email.
Okay, thank you again.
Thanks, everyone. Have a good one.